Oh my gosh, Michael Faraday himself asked such a brilliant question. How do capacitors work in series? How do capacitors in series and parallel work? And I think he misspoke parallel there. You know, great electrician, but probably not the best English student. We're going to talk about that. We're going to talk about how do capacitors work in series and parallel. And what does series and parallel even mean? Well, if you think about, let's say we have a little bit of a battery going on here, and we have, let's say we usually have like one capacitor. So this battery is 36 volts, right? You know, we can figure out, like, okay, let's say we know it's capacitance. We can figure out the amount of charge on this plate because we know capacitance is equal to the amount of charge on the plate for, you know, something like a parallel plate, or over the electric potential difference, the voltage, and the battery is 36 volts. It's going to apply 36 volts of voltage there. So then if we know a capacitance, maybe it's like, I don't know, 6 microfarads, named after this guy himself, you know, you could solve for the amount of charge. It gets a little bit more tricky when you have something like this. So we're going to kind of have two examples of each. So maybe you have something like this, right? So maybe this is 36 volts still, and we're dealing with, I don't know, 3 microfarads each. And, or maybe we're dealing with something like this. Where these are also 6 microfarads. Or maybe we'll say this is, I don't know, 12 microfarads. I don't know. It could be anything, really. So what I'm drawing right here is what we mean by series and parallel. So we have series, which is when you have two capacitors lined up series by series. So this is our top plate and bottom plate. Then the bottom plate is connected with this guy's plate. And then that connects back to the battery. That's what we mean by series. Anytime you kind of see two plates linked up together, that's really a series. And, you know, we'll talk more about series, and we have parallel right here. Parallel is when they're parallel together, where each plate is connected to the battery. So that is what we mean by parallel. Let's say we're trying to figure out how much charge is on each plate. It's a little bit harder than just doing C equals Q over V, right? Because that's the equation for one capacitor. We can't just plug in like 3 microfarads plus 3 microfarads into here, right? Because what that is suggesting is that, hey, these two capacitors have this, if you were to add them up, they have the same capacitance as this guy right here, just one right there. And the reason that's not really true, okay, and I'm actually going to dive into the reason why we can't just make that assumption here. Actually, I'll just get started with series. We're going to derive the equation together. So, capacitor in series. I'm going to kind of blow this thing up and make it a lot bigger. So we kind of know what we're talking about. You know, there we go. So, you know, we have 36 volts here. Now, what's going to happen when we plug this whole thing into the battery, one key point in deriving the equation for the equivalent capacitors, which is what we're trying to do. The equivalent capacitor is like, hey, what capacitor can do the same job as these two capacitors, where if I were to take this equivalent capacitor, it would make no difference, you know, substituting it for that equivalent capacitor. And we're going to try to figure out why it's not as simple as 3 plus 3, and we're gonna figure that all out. First thing you got to understand, obviously, each of these plates are going to have charge. So as we plug this in, you know, remember, it's always negatives flowing the other way, but we can model it as positive charge flowing this way. So we're going to get some positive buildup of charge here. I'm going to call this Q. What do we know has to be true? Well, this will have to be negative Q. how do we know that? Well, because for each amount of positive charge here, you gotta have the same amount of negative charge here for the electric field lines to kind of match up, and for us to get kind of that constant electric field in between them. Okay, well, there's going to be a certain amount of charge in here. I don't know how much. Maybe in the wire and the plate, maybe in the wire we're going to have, I don't know, Q total, whatever. There's really going to be no net charge in here, this wire. So because of conservation of charge, if you're going to have negative Q in here, you got to have Q in here. And by the way, as I'm explaining this, if I'm explaining any of this wrong, please let me know. This is actually what I'm learning right now. Helps me to just kind of explain it. So if there's any people that know what they're talking about, please let me know if I'm getting any of this wrong. But to my understanding, hey, if you gotta have negative Q here, the negative Q is gonna kind of get over here. You're gonna be left with positive Q here, right? So if you think about all the total charge here, if you get negative Q away, you're left with positive Q. So, and it's the same deal here. You're gonna get negative Q as buildup right here. What did we just figure out? Well, each plate is going to have the same amount of charge, right? Each plate is going to have the same amount of magnitude of charge. This is true for no matter how many series connections you got. So if you have even something like this, guess what? Negative Q, oh well, in order to get that negative Q, you got to have a Q here, and then you're going to have a negative Q here. This is true for all series. Because of how, because of conservation of charge and how, they kind of polarize here and get negative Q and then positive Q on one side, which is pretty neat, to be honest. So, how is this helpful? Well, we know the equivalent capacitance. So let's say the equivalent capacitance is going to equal, well, the charge over the total voltage. So whatever the equivalent capacitor is, it's going to have the same charge as any one of these little thingamabobs. It's going to have the same amount of... Actually, wait, what am I doing? What am I doing with my life? That's not how I want to explain it. Don't forget what I said. Before I get into equivalent capacitance, we're going to talk about voltage. How does voltage play a thing in here? Well, kind of intuitively, you can figure out that the total voltage here, it's going to equal the voltage here, V1, the voltage here, V2, then the voltage here, V3. So the total amount of voltage is going to add up to 36 volts. Alright, how is that useful? Well, what we can say is that, okay, V1, so V1 is going to equal, or V1 plus V2 plus V3 is going to equal the V total, 36 volts. Awesome. Now, what is V1 equal to? Well, we know that for any capacitor, so we're going to say this is C1, C2, C3. C1 is going to equal Q over V1. C2 is going to equal Q over V2. C3 is going to equal Q over V3. So, in this case, you can solve for the V3 by just kind of, or V, whatever, you can just kind of swap those, right? So, multiply by V1 divided by C1, you really get V1 is equal to Q over C1. V2 is equal to Q over C2. V3 is equal to Q over C3. V3 is equal to Q over C3. I just did algebraic manipulation for that. And then I can just plug everything in here. So Q over V1 plus Q over V2 plus Q over V3 is equal to V. One really nice thing is then I can, why am I writing V1? I'm so sorry, you're probably so confused. C1, I'm doing C1 because I solved for V right here, so that was my mistake. But hopefully this makes sense how I'm doing this whole thing. So, Q, so let's factor out a Q here. We're going to get 1 over C1 plus 1 over C2 plus 1 over C3 is equal to V. And then we can divide the whole thing by Q, and then what we're going to see is we're going to get 1 over C1 plus 1 over C2 plus 1 over C3 is going to equal V over Q. You know, so V over Q, what is V over Q? Well, remember, C is equal to Q over V. So whatever our equivalent capacitor is it's going to have, so our equivalent capacitor, remember, so if we think about back here, let's just say C, this is, I'm not going to say 6, because, you know, I'm about to show you why it's not going to be 6. But let's say that is the equivalent capacitor right here, where when you replace this, this amount, so what I'm saying here is this is the equivalent capacitor that you could replace these two and just put in one capacitor right there. Let's say this is our equivalent capacitor. Well, the equivalent capacitor is going to be running through this amount of voltage. So C equivalent is going to have 36 volts, right, what we just solved for. And then if we just take the reciprocal, right, Q over V, the reciprocal of that is V over Q. I'm sorry for the lawnmower, by the way. The reciprocal of C over EQ, or let me repeat that. The reciprocal of C equivalent, C equivalent is going to be 1 over C equivalent. V over Q, that's just what we solved for. So V over Q is the same as 1 over C equivalent. What does this tell us? Well, that tells us that if you want to find the C equivalent for this kind of a scenario, you got to add up the reciprocals of all of your capacitors and then take the reciprocal of that again, right? So for example, if this was 12 and this was 4 and this was 6, right? You do 1 over 12 plus 1 over 4 plus 1 over 6. You can do the fraction math in your head. I don't really want to deal with that right now. But whatever you add up, so let's say you do 1 over 12 plus 1 over 4 plus 1 over 6, you gotta take the reciprocal of that, right? So whether it's 1 over 12, 1 over 6, 1 over 4, let's just say it's 1 over, I don't know, 3. I don't know what the fraction math is. But then if I get 1 over 3 is equal to 1 over CEQ, you're not done yet, right? That 1 over 3 is not the equivalent capacitor. You got to take the reciprocal of that again. So hopefully that makes sense. So for example, I'm actually just going to show you with actual numbers. Let's say C1 is 4, C2 is 8, and then C3 is 12. Okay, let's just, kind of figure out the fraction math in our head. This is actually a really bad example. Okay, let's just say this is 4, just for simplicity. Doesn't really matter here. So then we can just change this to 2 over 8, right? Just doing the fraction math. So I would get 5 over 8. But 5 over 8 is not the equivalent capacitor, it is 8 over 5. Because 5 over 8 is equal to 1 over C. So you got to take the reciprocal again. I'm going to be right back. I'm probably going to make this a part 2. I just got to really quickly do something. So this is capacitors in a series. Thank you for watching.